In 1926, Erwin Schrödinger, an Austrian physicist, took the Bohr atom model one step further. Schrödinger used mathematical equations to describe the likelihood of finding an electron in a certain position. This atomic model is known as the quantum mechanical model of the atom. Unlike the Bohr model, the quantum mechanical model does not define the exact path of an electron, but rather predicts the odds of the location of the electron. This model can be portrayed as a nucleus surrounded by an electron cloud. Where the cloud is most dense, the probability of finding the electron is the greatest, and conversely, the electron is less likely to be in a less dense area of the cloud. Thus, this model introduced the concept of sub-energy levels.
An orbital is a region in space around the nucleus where there is a high probability of finding an electron. Each electron in an atom is characterized by 4 quantum numbers: the principal, azimuthal, magnetic, and spin quantum numbers.
The principal quantum number n determines the energy and size of an orbital.
As the principal quantum number, n, increases, the size of orbital becomes larger. Hence, the energy of the electron increases.
The next quantum number, the azimuthal quantum number or angular momentum quantum number, L, defines the angular momentum, which is the basic quantity characterizing the motion of an electron around a nucleus. Thus, it describes the shape of an orbital. It can assume integral values from 0 up to n-1.
For example, when n equals 1, L has the value of 0. Thus, the orbital is 1s. When n equals 2, L has the values of 0 and 1. Thus, the orbitals are 2s and 2p respectively. The 1s orbital has lower energy and smaller size than the 2s and 2p orbitals.
The magnetic quantum number defines the spatial orientation of the orbital angular momentum and the spatial orientation of orbitals in relation to each other. The values of m are dependent on the value of L. The number of these values, 2L plus 1, equals the number of orbitals. For example, when L equals 1, m equals minus 1, 0, 1. Thus, there are 3 values of m, or the number of p orbitals is 3, oriented along the x, y, and z axes. Let us consider the first quantum level, whose principal quantum number, n, is 1. There is only one s orbital in this level, because the value of the azimuthal quantum number L is 0, and the magnetic quantum number m is 0. This orbital is labelled 1s. The number 1 refers to the value of n. Thus, there is only one orbital in the first quantum level. The maximum number of electrons in this quantum level is 2. The principal quantum number for the second quantum level is 2. There are s and p orbitals in this level, because the values of the azimuthal quantum number L are 0 and 1 respectively. There is one s orbital, since the magnetic quantum number for L equals 0 is 0. This orbital is labelled 2s. In addition, there are 3 p orbitals, since the magnetic quantum number for L equals 1 is -1, 0, 1. These orbitals are labelled 2px, 2py, and 2pz. Thus, there is a total of 4 orbitals in the second quantum level, each of which can accommodate 2 electrons, giving a total of 8 electrons. In a similar way, we will find out that in the third quantum level, there are 1 s orbital, 3 p orbitals, and 5 d orbitals. The total number of orbitals is 9, and the maximum number of electrons is 18.
The last quantum number, the spin quantum number, arises from the opposite direction of an electron's rotation on its own axis, spin. There are only 2 possible values, +1/2 and -1/2, which correspond to the opposite rotation directions.
For the s orbital, a spherical electron distribution is obtained. Within the p subshell, there are 3 orbitals of identical shapes, dimensions, and energies, differing in their spatial orientation. They are respectively referred to as p sub x, p sub y, and p sub z orbitals. Their nodal planes are respectively the yz, xz, and xy planes. Now, let us study the 5 orbitals constituting the d subshell. All d orbitals have the same energy. 4 of them have the same shapes, but different spatial orientation. They exhibit 4 maxima and slightly resemble a clover leaf in shape. Only the d sub z squared orbital has a different shape, and just 2 maxima, pointing along the z-axis. The d sub x squared sub minus y squared has 4 maxima, pointing along the x and y axes.